All right, welcome back. Week 2, lesson 2. You guys are doing awesome. Today's topic is electrochemical cells. And before we get started, we're going to do our mindful minute. So you may sit with a mindful body, making sure your head, neck, and spine are aligned. And I invite you guys to close your eyes, or you can watch the animation on the screen. And we'll take deep breaths together for 1 minute. Everybody, inhale. Inhale through your nose and exhale. Inhale, nice deep breath in. And exhale. Deep breath in. Exhale. We're halfway there. Deep breath in, taking that energizing oxygen. Exhale, releasing stress and tension. Inhale, energizing oxygen. Exhale, releasing stress and tension. Last one, deep breath in. And releasing stress and tension as you exhale. Allow your breathing to return to normal. And when you're ready, you can slowly blink open your eyes. Okay, so today's learning target is I can explain how an electrochemical cell works. Pause the video now so that you can write down this learning target. All right, for our do now, we're going to review oxidation reduction and oxidation states. So our question is, given the equation representing a reaction, which half reaction equation represents the oxidation in the reaction? So let's annotate for some keywords here. We're looking for a half reaction. Okay, those are our options down here. How do we know these are half reactions? Take a look at them. Well, it only shows one element and they show electrons, so we know it's a half reaction. And we're looking for oxidation. So oxidation is what? Oxidation is losing. Actually, I think I have, there we go. We have oil rig to remind us that oxidation is losing. So we can actually eliminate some of these options right away. Can you guess which ones? Well, we can eliminate anything that doesn't appear to be losing electrons. So if something is losing electrons, it's on the right side of the equation. So our answers could be 2 or 3, and we can cross out 1 or 4 because electrons are on the reactant side and they're being gained. So we know it's not those. So now how do I know which one is the right answer for what's happening in our reaction up here? So I need to find out what's being oxidized. Is the cadmium being oxidized or is nickel being oxidized? So let's isolate our half reactions. Cadmium from here to here and nickel from here to here. What's my oxidation state on cadmium? Well, it's by itself, so I know the oxidation state is 0. And over here, I'm not sure because it has this OH and 2 of these OHs next to them. So whenever you see these parentheses, that means it's a polyatomic ion because we want to group the polyatomic ion together and not get it confused. So there's 2 OHs. So how do I know the charge on this? Well, we can use our reference table. We can go to table E and we can look for OH. OH is over here. It's called hydroxide. So hydroxide has what kind of charge? Its overall charge is -1. So I'm going to remember that as I go back to my question. So with knowing that OH has a -1 charge, and we see that there's two of them, so this gives us a -2 overall, cadmium must be a +2. Okay, let's find out what's happening with nickel. Nickel's with oxygen. The rule for oxygen is the oxidation state is always -2. There's two of them, so that must mean that this gives us a -4 overall. And what must nickel be? Well, it must be +4. Okay, what about down here? OH we determined has a -1. There's two of them, it overall has a -2. And then nickel must have a +2. So looking at both half reactions, cadmium is going from 0 to +2. Is it being oxidized or is it being reduced? Its charge is going up, so it's losing electrons. And we remember that oxidation is losing. So this is what's being oxidized. And if we look at nickel, it's going from +4 to an oxidation state of +2. So its charge is going down. We know that nickel is being reduced. So going back to our options, wow, my handwriting. Going back to my options, it can't be this because nickel is actually being reduced, and this actually isn't even correct then. So it must be cadmium. We said that cadmium is going from a 0 to a +2, and we see that here, and it's achieving that by losing 2 electrons. Okay. So for today, we're going to look at electrochemical cells and how they work. What is an electrochemical cell? Well, any battery that you have is an electrochemical cell. That means it takes chemical energy and it converts it to electricity. So, electricity is actually a chemical reaction. So, we're going to find out how that works. And I encourage you guys to take notes during this time. And remember that you have check for understanding questions that go with this video.
In this video, we're going to talk about galvanic cells, which are also called voltaic cells. So what are they? Well, galvanic or voltaic cells are devices that use a chemical reaction to create electricity. Specifically, the type of chemical reaction that they use is called an oxidation reduction reaction. But we'll talk more about that later.
So basically, any battery that you have is using oxidation reduction reactions to make it work. Ta-da!
Now, galvanic or voltaic cells may be totally new terms for you, but I'm willing to bet that you use these devices almost every single day of your life. And that's because a battery is an example of a galvanic or voltaic cell. There are chemicals inside batteries, and those chemicals react together in an oxidation reduction reaction that makes electricity. And this is what powers your cell phone or your flashlight or whatever the battery is hooked up to. So let's learn more about these devices and see how a chemical reaction can create electricity. Okay, so I think for the rest of this video, I'm just going to call these voltaic cells instead of calling them galvanic or voltaic cells. All right?
So I call them electrochemical cells because that's what it says on the regions a lot of times. Rarely will it say galvanic cells, so it'll either be electrochemical or voltaic cells.
I now want to talk about the parts of a basic voltaic cell, one that you could actually make in the lab. So here's what they are. First, we start with two beakers or containers of water. And into one of them, we dissolve some zinc sulfate to make a solution. And then into the other, we dissolve some copper sulfate and make a solution with that. So we got these two solutions. Then we take a piece of zinc metal, like this one right here, and put that in the zinc sulfate solution. And then over here, we take a piece of copper metal and we put that in the copper sulfate solution. The next thing we do is we take a wire, a metal wire, and we use that to connect the two pieces of metal together. And when we do this, something amazing starts happening. Electrons start moving through this wire. They move from the zinc metal into the copper metal. Now, this is a big deal because moving electrons are what make electricity. So when we hook this wire together with the pieces of metal and electrons start moving through it, we have electricity. We have electricity moving through this wire. And what we could actually do is we could take a little light bulb like this and hook it up to this wire, and the light bulb would turn on because there's electricity moving through this wire. Now, to be really specific, there's one more part of the voltaic cell, and that's a little tube called a salt bridge that connects these two solutions. We'll talk more about the salt bridge at the very end of this video, but right now I'm going to leave it out because I want to make sure that we keep things simple. So this is the basic setup of a voltaic cell. Now, I want to zoom in so that we can see the atoms and electrons in the metal and in the solution and understand what's causing electrons to move along this wire and create electricity. Here's our magnification of the different parts of the voltaic cell. We can see some of the atoms in the metals and in the solutions. So let me show you what's what. This is a magnification of the area here. These zinc atoms are on the edge of the piece of the zinc metal. And then these Zn2 plus ions are in the solution. They're part of this ZnSO4 solution. I'm not showing the SO4 here. I just want to focus in on the zinc. So zinc ions in the solution and these zinc atoms in the piece of zinc. Then over here, we have these Cu2 plus ions that are in the CuSO4 solution. They're dissolved here. And then these copper atoms are on the edge of this piece of copper here. Okay? So we've got a wire that connects the zinc and the copper. And we've said that when we hook everything together, electrons start flowing through this wire. Well, why is that? Well, when we connect these two pieces of metal with a wire, it kind of starts a tug of war between the zinc and the copper. They're having a tug of war for the electrons. One of them wins and one of them loses. It turns out that Cu2 plus, these atoms here, Cu2 plus has a really strong pull for the electrons. But then on the other hand, zinc, these zinc atoms, zinc has a weaker pull for electrons. So in this tug of war, Cu2 plus ends up winning.
So recall, what is a pull for electrons? What is the vocab word that describes that? That question's in your check for understanding.
Let me show you how this happens. So Cu2 plus really wants electrons. So it's kind of like it calls over here to zinc, which has a weaker pull on the electrons, and says, hey, zinc, give me some of your electrons. And zinc's kind of weak, so it's like, oh, okay. And what happens is, let's say this zinc atom here gives away two of its electrons. And these electrons enter the wire and move towards the copper. Now, when zinc gives away those two electrons, it causes its charge to change. It's lost two electrons, so it gets a positive charge, and it becomes Zn2 plus. Now, changing from neutral zinc to zinc 2 plus has a big effect on this atom. And that's because neutral atoms make up solid metal, but metal ions usually dissolve in water. So after this zinc atom turns into Zn2 plus because it lost these electrons, it's no longer part of the solid metal anymore, and it floats off, it dissolves into the solution. Okay, so that's what happens to the zinc. Then over here, these electrons make their way down the wire to the copper, and one of these Cu2 plus ions, which really wants electrons, is going to come over here, and these two electrons are going to be added to the Cu2 plus ion. Gaining these two electrons is going to get rid of that 2 plus charge that was on the copper. And that is going to turn it into a neutral atom, which means that it is no longer going to be able to dissolve in solution, and it's going to become part of the solid copper metal here. Okay? So that's what happens to the copper. Now, notice that for this whole process to happen, electrons have to move through this wire. And that's where the electricity, the electron movement comes from. Let's see that one more time. So zinc loses two of its electrons here. Those move through the wire. Loss of those two electrons causes zinc to take on a 2 plus charge. It is then going to dissolve in the solution. These two electrons are going to move over here to copper. And one of these Cu2 plus ions that really wants electrons is going to come, it's going to take them in, and that is going to get rid of the Cu2 plus. It's going to get rid of the 2 plus charge, and this neutral copper atom is now going to become part of this solid piece of copper metal. So that is where this electron movement through the wire is coming from. Zinc loses these two electrons. They move through the wire, creating electricity. They come over here and they join up with the Cu2 plus, turning it into neutral copper. We have these electrons moving through the wire here, creating electricity. So that is how we get electricity, from these electrons moving from the zinc over here into the copper. And if
I just want to point out that the flow of electrons, it's important to know which direction they go from and to. So in your homework, you'll have a question about determine which direction the electrons will flow. So we know that because one is being oxidized, losing electrons, and one side is being reduced, gaining electrons. So just keep that in mind.
If this happens long enough, we actually see these two pieces of metal change, right? Like these zinc.
Sorry that I keep pausing the video, but I want you guys to predict, what do you think the change would be over time? If this continues to run, what would happen to the zinc over time, and what would happen to the copper over time? Let's find out.
Zinc atoms keep coming off of this piece of zinc. So it's essentially dissolving. And over time, what we'll see is that this piece of zinc actually starts to dissolve. It gets smaller and smaller. But then on the other hand, those Cu2 plus ions are coming out of solution and are attaching to the solid copper. And so they're going to make this piece of solid copper bigger and bigger. And so if we let this voltaic cell run for long enough, we'll eventually see that these two pieces of metal actually change size and shape. Here are some diagrams for the process that's happening in the voltaic cell. I want to describe what's going on in terms of oxidation and reduction. So over here, one of these neutral zinc atoms is losing electrons. So that means that oxidation is happening on this side of the voltaic cell. And over here, this Cu2 plus ion is gaining 2 electrons to turn into a neutral copper atom. So reduction or gain of electrons is happening over here. Now, we can give names to these two parts of the voltaic cell based on whether oxidation or reduction takes place. So the cathode is the name that we give for the site of reduction, where reduction happens. So reduction is happening here, which means that the piece of copper is the cathode, the site of reduction. And the piece of zinc over here is where oxidation is happening. So the piece of zinc is going to be the anode. So reduction at the cathode on copper, oxidation at the anode on zinc. Now, let's write reactions for the two processes that are happening here. Okay? First, let's write the reaction for reduction.
So he's about to write the two half reactions that occur. I encourage you guys to pause the video, try it on your own, and then start the video and see if you got it right. So you'd be writing the half reaction for copper and the half reaction for zinc.
We're starting with Cu2 plus, and this Cu2 plus is dissolved in solution. So I'm going to write that with an AQ for aqueous after it to show that it's dissolved in solution. Now, this Cu2 plus gains 2 electrons, so I'll write plus 2e minus, and that gives us a neutral copper atom. So I just write Cu with no charge after it. That shows that it's neutral, and then it's part of the solid metal, so I write an S after it. So this is the reaction for the reduction process. Over here, the reaction for the oxidation process. We start out with a neutral zinc atom, and this neutral zinc atom is part of the solid piece of zinc. So I'm going to put this S here for solid. Now it loses 2 electrons. To show that we lose something in a chemical reaction, we put it on the other side of the arrow. Okay? So I'm not going to write anything right here. I'm going to put this arrow. I'll leave the electrons for last. Losing the electrons turns the neutral zinc atom into a Zn2 plus ion, Zn2 plus, that is now dissolved in solution. So I'll write AQ here. And then finally, to show that I lost those 2 electrons here, I'll put plus 2e minus on this side. So this is the reaction for the oxidation. Now, these 2 reactions that I wrote, we call them half reactions because each one of them tells half the story of the oxidation reduction process. And we can actually give names to these 2 parts of the voltaic cell as if each one of them is half of the big picture. We call this the oxidation half cell. It's half of the voltaic cell where the oxidation is taking place. And we call this the reduction half cell. It's half of the voltaic cell where reduction is taking place. And it is these half reactions that show what's going on in each one of the half shell, in each one of the half cells. I said half shells. It's like Teenage Mutant Ninja Turtles coming back to haunt me from the 80s. Anyway,
I apologize for his joke. Anyways,
we have these 2 half reactions, and we can put them together to get a net ionic equation, which shows the overall oxidation and reduction process. We start with solid neutral zinc and Cu2 plus ion, and then at the end of the process, we're left with zinc 2 plus ion, and then we have solid copper. This is the net ionic equation that we get from adding together these 2 half reactions.
okay, I'm going to fast forward because this part is not relevant for us. Okay, now he's going to circle back to what this salt bridge does. So what's the purpose of that little piece connecting the 2 cells?
what the salt bridge is, what it does, and why it's important in a voltaic cell. The salt bridge helps to balance out charge in the voltaic cell. Here's what I mean. The two solutions are made up of both positive ions and negative ions. I didn't show the negative ions before. Those are these yellow things. I just showed the zinc and the copper. But along with these metal ions are these polyatomic ions, sulfate, SO4 2 minus. It's a sulfur with 4 oxygens, and the whole thing has a 2 minus charge. I didn't want to have to keep using this thing, so I've just abbreviated these as SO4 2 minus. But the point is, the negative charge from the sulfate balances out the positive charge from the zinc or from the copper. So right here in my two half cells, the charges are balanced out. But let's look at what happens as the voltaic cell begins to run for a while. Okay? Over here, these zinc atoms are going to give electrons to copper. So they are going to end up with a charge. I'm not showing the electrons here, but electrons are getting sent up here as these turn into Zn2 plus ions and as they enter the solution. Now over here, as electrons come over, these Cu2 plus ions will turn into neutrally charged copper atoms and attach to the metal. Now, look at what's happened to the charge here, okay? Now we have all of these Zn2 pluses, but we have only a few of the SO4 2 minuses. So after just a little while, positive charge really begins to build up in this half cell. And then over here, as the positively charged ions like this lose their charge by gaining electrons and turn into neutrally charged copper, now there are a whole lot more SO4 2 minuses than there are Cu2 pluses. So a negative charge begins to build up on this side.
Just a note, you may be thinking, why can't the SO4 2 minus travel through the wire? The only thing that can travel through the wire is electrons.
And if this positive and negative charge build up too much, the cell can't run anymore. It can't continue to make electricity. So that is where the salt bridge comes in. Let me get rid of this wire and show you what the salt bridge looks like. Here is the salt bridge. It is a tube shaped like an upside down U that, in our case, is filled with sodium chloride. And you can see the Na plus and the Cl minus ions. Now, at the ends of the salt bridge, there are cotton plugs, a little bit of cotton there. And the cotton prevents the solution from just pouring out into the half cells. But these ions are able to slowly pass through the cotton plugs, and here's what happens. We said that negative charge is going to start building up in the half cell over here. And so the positively charged Na plus, is going to begin moving over into this half cell to help balance out the charge. So the Na plus ions are going to begin moving in this direction to balance out the negative charge. And over here, we said that positive charge begins to build up. The Cl minus ions are going to begin moving through the salt bridge to come out through the cotton and help to balance out the positive charge that builds up on this side of the voltaic cell. So over time, what we're going to see is we're going to see that the Cl minuses move in this direction to balance out the positive charge that builds up here. And then we'll see that the Na pluses begin to move to this side to balance out the negative charge that builds up here. A salt bridge helps to balance these charges to make sure that they don't build up too much, and that would prevent the voltaic cell from being able to work. Wow, so we just learned so much about galvanic or voltaic cells. Okay, so here's the basic structure. of a voltaic cell. We have the zinc sulfate solution here, copper sulfate solution here. We have zinc metal and copper metal. Now, when we hook this all together, electrons start flowing from the zinc to the copper. And that's because copper that's in the solution has a strong pull for electrons, whereas the zinc has a weaker pull, so the copper wins. As electrons move from the zinc to the copper, they are lost in the zinc, so oxidation takes place, and they're gained here in the copper, so reduction takes place over here. We call this the oxidation half cell, and we call this the reduction half cell, because oxidation is happening over here. The piece of zinc is the anode. Because reduction is happening over here, the piece of copper is the cathode. Then finally, we can write half reactions for the two processes that are happening in the different half cells. Here is solid zinc losing 2 electrons because they're moving out to turn into a zinc 2 plus ion, which is going to enter the solution. And then over here, Cu2 plus ion that's in the solution gains 2 electrons and turns into solid copper. It's going to attach to this metal right here. And then finally, we can sum all of this up by writing this cell diagram or cell notation, which shows everything that's happening in a shorthand abbreviated form.
So that part we didn't cover, so I'm going to stop here. I will also link this video in the assignment for this week if you want to just watch this video. All right, so you can either pause, try your check for understanding questions. You can do those at the end. We just did a lot, so I encourage you guys to take a break for like 2 minutes right now, and then come back. Don't take too long of a break. Okay, so our definition for a voltaic cell, which is a type of electrochemical cell, is a mechanism that converts chemical energy to electrical energy to conduct electricity through the flow of electrons. It's considered a spontaneous redox reaction, meaning it uses oxidation reduction. And oxidation occurs at the anode of the cell, and reduction occurs at the cathode of the cell. Pause the video now so that you can write down this definition. Now, one way to remember where does oxidation and reduction happen is this fun mnemonic. So our mnemonic is red cat and an ox. So what does red cat and an ox mean? Well, reduction happens at the cathode and oxidation happens at the anode. So it's the beginning part of each of those words. Again, reduction happens at the cathode, oxidation happens at the anode. So if you get kind of confused, you use red cat and an ox, similar to how we used oil rig. And another definition we have is salt bridge, which connects the two half cells and allows ions to flow freely between the two. And this balances out the charge. Pause the video now so you can write down this definition. All right, we'll do a few check for understanding questions and an open response question. During an oxidation reduction reaction, the number of electrons gained is blank. 1 equal to the number of electrons lost, 2 equal to the number of protons gained, 3 less than the number of electrons lost, or 4 less than the number of protons gained. So we're talking about oxidation reduction, which is the movement of electrons. So which options can we cross out right away? We can cross out 2, and we can cross out 4, because we're not talking about protons here. Now, whenever an electron is gained and it moves through the wire, what happens? Where does it go? So whenever an electron is gained, where is it coming from? Well, it's coming from the other side of the cell where electrons are being lost. So for every one electron gained, that means there's one electron being lost. So our answer is 1. Okay, next question. Where do reduction and oxidation occur in an electrolytic cell? 1, both occur at the anode. 2, both occur at the cathode. 3, reduction occurs at the anode and oxidation occurs at the cathode. Or 4, oxidation occurs at the cathode. Reduction occurs at the cathode and oxidation occurs at the anode. So these are getting kind of confusing for me. How do I remember which is which? Well, we can remember red cat and what's the other one? And ox. So reduction at the cathode and oxidation at the anode. So our answer is 4. Okay, now we're going to try an open response question. So this one says a student sets up a voltaic cell using magnesium and zinc electrodes. The porous barrier in the cell has the same purpose as a salt bridge. So that's referring to this part right here. The diagram and the ionic equation below represent this operating cell. Okay, so we have magnesium over here, zinc over here, a salt bridge, and then we have an equation at the bottom. So our question is, determine the number of moles of Mg2 plus aqueous ions produced when 2.5 moles of zinc 2 plus aqueous react completely in this cell. So we haven't learned moles yet, but we can still answer this question. How many moles of Mg2 plus is produced when 2.5 moles of Zn is reacted with? What do you guys think? We have Mg being produced and zinc is being reacted with. So it's just like the electron question before. If there are 2.5 moles of zinc reacting, that means that there must be 2.5 moles of Mg being produced. So your answer would be 2.5 moles. Moles is a unit of measurement, which we will cover in a later unit. So number of electrons lost equals number of electrons gained. Number of moles used equals number of moles produced. Okay, next question. State in terms of ions how the porous barrier functions as a salt bridge in this cell. So state, and we have to include in our answer ions, how the porous barrier functions as a salt bridge. So we have to think, what does a salt bridge do and what does it have to do with ions? Our salt bridge is responsible for balancing charge by allowing ions to move freely. So remember that it prevents the buildup of charge, which would ultimately stop the cell from working. So the ions are allowed to move freely through here so that it can balance out the charge and continue working. All right, last question. Write a balanced half reaction for the oxidation that occurs in this operating cell. So we must use our reaction down here and figure out what is being oxidized. So let's isolate our two elements, Mg and zinc, Zn. So what charge does Mg solid start with over here? Well, it starts with a 0 charge because it's by itself, and it's going to a, hopefully you guys can see that, it's going to a +2 charge. So what's happening to magnesium? Is it gaining or losing electrons? It's losing electrons. So this is our oxidation. So what would be the half reaction? Remember that we have to start with Mg on one side, Mg2 plus on the other. And the important part is, where do I write my electrons? Do they go on the left as a reactant, or do they go on the right as a product? We know that oxidation means what? Losing. So our electrons are written on the product side. And how many electrons are being lost? It's going from a 0 oxidation state to a +2, so that means 2 electrons are being lost. So there's our half reaction. Okay, good work today, guys. This was a longer lesson than usual. For your assignment today, you're going to go to part 4, assignment 2, and you have this worksheet, and it gives you 2 regions questions based on electrochemical cells. Now, to make it a little easier, I did a video on how to complete this worksheet where I read through the questions and I give you some hints. So it says right next to the assignment, directions for how to do assignment 2. I recommend you watch this. It's about 6 minutes long, and it'll really help you with understanding these questions and how to answer them. All right, thank you guys, and I will see you next week. As always, email me if you have any questions. Take care.